Have you ever really thought about what goes into a modern air defense system? It's so much more than just missiles. It's really this incredible symphony of advanced engineering, right? You've got radar that can see for hundreds of miles, communication that's faster than lightning, and processing power that makes life or death decisions in a split second. It's a fascinating technological puzzle. So let's start with the big question at the heart of it all.
I mean, seriously, think about that. That's the core engineering problem right there. We're talking about defending huge, massive areas against targets that are moving at thousands of miles per hour. How on earth do you even start to design a system that can see, track, and then respond, all in the blink of an eye? Well, the answer isn't one single superweapon. It's actually a much smarter, more strategic concept.
And that solution is what we call a layered defense. The best way to picture it? Think of an old medieval fortress. You don't just have one big wall, right? No way. You've got a moat way out there to spot trouble from a distance. Then you have your strong outer walls as the first real line of defense. And then, for anything that manages to sneak through, you've got your guards right inside the castle. Each layer has a very specific job, and the whole thing only works if they all communicate perfectly. So let's take a look at the tools that build these layers. Okay, so what are the actual pieces of hardware that make up these defensive layers? Let's break down 3 of the key systems, because each one is designed for a very specific role in this whole strategy. So here's kind of how those layers stack up. You've got the S-400 Triumph, that's your long-range workhorse. It uses powerful radar and missiles that rely on radio frequency or RF guidance. Basically, it's homing in on the radar echo bouncing off the target. Then you've got the next-gen S-500 Permiti, which is designed to go after things at even higher altitudes and higher speeds. And finally, you have the Pantsir S-1. Think of this one as the close-in bodyguard. It's a point defense system that uses its own radar and electro-optical cameras, thermal and TV, to protect the bigger systems from any last-minute surprises. Each one is a specialist, and each one is a crucial part of the network. But here's the thing. None of these missile systems can do a single thing without their eyes and ears. The absolute, unseen foundation of all modern air defense is radar. It is the technology that lets these systems see and understand the world around them. At its core, how radar works is actually beautifully simple. The system just sends out a powerful pulse of radio waves. That pulse travels out, it hits something, and then a tiny, tiny fraction of that energy, the echo, bounces back. By measuring how long it took for that echo to come back and which direction it came from, the system can figure out the target's distance, its speed, and its location. It's basically just a really, really high-tech game of Marco Polo. Of course, modern systems are way more advanced than that. Instead of some old spinning dish you see in the movies, they use something called a phased array antenna. These things can steer radar beams electronically with literally no moving parts. What that means is they can scan the sky almost instantly, jumping from one target to another, and, this is the crucial part, they can track dozens and dozens of them all at the exact same time. But here is the real kicker. The sky is incredibly noisy. You've got radio waves from everything, you've got weather, you've got birds, you name it. So the true engineering genius isn't just in sending and receiving a signal. It's in being able to pick out the incredibly faint echo of a real threat from all of that background junk and any intentional jamming. So how do you find that tiny needle in a massive, noisy haystack? Well, that's where the brain of the whole operation comes in: signal processing. This is what takes all that raw, messy data from the radar and turns it into something you can actually use. And doing this takes a staggering amount of computational horsepower. To sort through all that noise and track a bunch of high-speed targets in real time, we are talking about trillions of calculations every single second. The processing power required is just immense, and its job is to turn all of that chaos into pure clarity. And this right here shows you the difference that processing makes. On one side, you've got the raw radar data. It's just a digital storm, a mess of signals and noise. But on the other side, you get the final product, a clean, identified target with a precise flight path. This is what allows the system to tell the difference between a stealth aircraft and a flock of geese in a fraction of a second. It literally turns a wall of static into a clear voice. And the unsung heroes that make all of this possible are the radio frequency or RF systems. These are the components that actually generate those powerful radar pulses and manage all the frequencies to try and cut through that interference. So if signal processing is the brain, then the RF systems are the powerful voice and the super sensitive ears that let it talk to and listen to the world. And remember, this is a layered defense. So all these different units, the S-400s, the Pantsirs, the command centers, they all have to be talking to each other instantly. This means you need communication links with incredibly low delay, what we call latency, and they have to be extremely reliable, because in a game like this, a single dropped message could be absolutely catastrophic.
So I think the most important thing to take away from all this is that these aren't just separate technologies bolted together. It is one deeply integrated network. Yeah, the radar systems are the biggest piece of the pie, but they are totally useless without the signal processing to make sense of the data, the communication links to share that data, and of course the guidance systems to act on it. Everything has to work as one cohesive unit.
All of this, as you can probably guess, leads to a constant state of evolution. Because the second a new defensive system is created, you can bet someone somewhere is designing new offensive technologies to try and beat it. It creates this endless, high-stakes engineering arms race. And the engineers who build these things are up against massive hurdles. The demand for faster and faster processing to track smaller, quicker targets, that never stops. The challenge of overcoming electronic jamming becomes this constant cat-and-mouse game. Just getting all these complex parts to work together seamlessly is a monumental task. And on top of all that, these systems have to work perfectly every single time.
So at the end of the day, the ultimate goal is to build a single intelligent network. It's to create a system where all the radar sensors, all the communication links, and all the processing brains work together like a single cohesive organism, one that's able to detect and respond to threats automatically and instantly across a massive area.
And that leaves us with one last, really fascinating question. In a world where we're seeing hypersonic missiles, stealth drones, and even swarms of AI-driven attacks, the targets are just getting faster and smaller and a whole lot smarter. So what's the next big leap in radar, or in processing, or in communication? Where does this incredible engineering race possibly go from here?